This is Mrs. Palmer-Quay with the third video for Module 9. In this video I want to talk about nonpolar and polar bonds and how they create nonpolar or polar molecules. Remember that an ionic bond is when electrons actually transfer themselves from one atom to another, where a covalent bond is that electrons are being shared between two atoms. Well, there are two more details that you need to know on covalent bonds. Covalent bonds come in two forms: nonpolar covalent bonds, which your textbook calls purely covalent, but most everybody else calls them nonpolar bonds, and polar covalent bonds. As you might guess, in a nonpolar covalent bond, electrons are shared equally between the two atoms, where in a polar covalent bond, they are not shared equally. If you think about the electrical charge, a nonpolar covalent bond has a balanced electrical charge around the entire bond, or around the two atoms that are involved in the bond, whereas a polar covalent bond has an unbalanced electrical charge where you have areas of negative and positive charges. To show this in a picture, first of all we have our nonpolar covalent bond, and here's one of our homonuclear diatomic molecules, our halogen, chlorine, and the bonding between these two atoms of chlorine is shared equally. And so there's no distinct positive or negative side. This is just all negative kind of all around, this electron cloud around those two chlorine atoms. In comparison, the polar covalent bond, like we have with hydrogen chloride, the chlorine has a higher electronegativity, so it's going to pull the electrons more than hydrogen will, and so electrons are going to spend more of their time on this side, shown by the blue. It's going to be more negative on the chlorine side and more positive on the hydrogen side. And then by comparison, in an ionic bond, the pull is so great, such as the one we have between sodium and chloride, that this electron actually leaves sodium and deposits itself around the chlorine atom, making a chloride ion. You won't be working with discrete electronegativity values in this course, but I wanted to let you know that there are numbers that have been determined of electronegativity for many of the elements in the periodic table, of which there's a sample here in this illustration. And you can see by looking at these numbers that in general the trends that we talked about, and that electronegativity increases as you move to the right across the periodic table, and it also increases as you move up the periodic table. That is being verified by the actual values that we see in this table for the most part, with fluorine, of course, occupying the highest negativity position here on the far right-hand corner. But you can see that to be a little more specific, we've got some values, some ranges of numbers, where when the difference between the two electronegativity values is less than 0.4, then the bond is considered nonpolar covalent. If it's between 0.4 and 1.7, then it's a polar covalent bond, and if it's greater than 1.7, it is a mostly ionic bond. So that really scientists are talking about covalent and ionic compounds in terms of their electronegativity differences, not always the metal-nonmetal comparison that we use in this course. So this is just extra information for you. You won't need to work with these numbers directly. Along with talking about bonds being nonpolar or polar, we also talk about molecules being nonpolar or polar. And there is a relationship between the types of bonds and the type of molecules. If you have nonpolar bonds in a molecule, and only nonpolar bonds, then you create a nonpolar molecule, and that seems pretty straightforward. But if you have polar bonds within a molecule, you can also create a nonpolar molecule if the shape is symmetrical and all the outside atoms are the same. If you think about this diatomic oxygen over here, as I mentioned with the chlorine, it's basically just this cloud of electrons all the way around the outside. So from an observer looking in on that particular molecule, it will just look like a big cloud of electrons. Well, this carbon dioxide molecule down here at the end does have polar bonds. Oxygen has a greater electronegativity than carbon, and so, electrons are being pulled more towards the oxygen. But really, all the way around the outside, all you're going to be seeing are these negative electrons. And so the molecule itself does not have a distinctive difference of positive or negative charge around the molecule. It's all negative as the same way that we saw around a diatomic. So that carbon dioxide, even though it's made up of polar bonds, is actually a nonpolar molecule. In contrast, polar bonds will create polar molecules if they are not symmetrical or if they do not have the same kind of atoms all the way around the outside. And the result is that one end of the molecule ends up being slightly positive and another part is slightly negative. And so we say the molecule itself is polar. Water is a good example of that. The oxygen, of course, has a very high electronegativity. It is greater than that of the hydrogen, and so the electrons are being pulled more towards the oxygen and away from the hydrogen. Since hydrogen is only one electron and one proton, this means we've got sort of a naked proton hanging out here in space, and that gives it a positive charge. And we use this delta plus to indicate it's slightly positive. This symbol here is the small version of the Greek letter delta. So polar bonds can create either nonpolar or polar molecules, depending upon how the atoms are arranged around the central atom. A molecule that has a positive and negative end, like water, can be called a dipole, and di, of course, means two. And we usually show that, or we can show that, by this little symbol here, which includes an arrow showing which way the electrons are being pulled, towards which atom that has a greater electronegativity, and then just a plus down at the other end where the atom will, or the molecule will have a slightly positive charge. When you have a group of polar molecules together, you can have dipole-dipole forces, which are weak attractive forces in between these molecules because of these weak positive and negative charges. And dipole-dipole forces are one example of intermolecular forces. There are several others, but you aren't responsible to know them for this course. Hydrogen bonds are one type of dipole-dipole force that you may have heard of in a previous class. They can be formed whenever hydrogen is bonded to oxygen, nitrogen, or fluorine because these three elements are quite electronegative and they tend to create that positive hydrogen nucleus sort of hanging out on edges of the molecules. Hydrogen bonding allows water to have its own unique capabilities, the capillary action that allows water to move through plants and up a paper towel when you're trying to clean up a spill, or the fact that water is liquid at room temperature when many other gases of the same mass are, or many other compounds of the same mass are gases, and also the fact that water in solid form is lighter, has less density than water in the liquid form. These characteristics are all due to hydrogen bonding. Hydrogen bonds also hold the DNA ladder together, so you can see how important this type of intermolecular force is to life. So here are some examples of molecules which contain polar bonds, but which are not necessarily polar themselves. The top three are all examples of polar molecules. We talked about hydrogen chloride and how the chlorine, being far to the right on the periodic table, has a greater electronegativity, so that it would be pulling electrons towards it, making a more negative end on the chloride end and a more positive end on the hydrogen end. Ammonia also, nitrogen has a very high electronegativity, and so each of these hydrogens would not have their fair share of that electron. They tend to be slightly positive, and the nitrogen would be more negative. Methyl chloride, this molecule on the far right, has again chlorine, that very electronegative halogen, and so the electron cloud would just sort of shift towards the chlorine, making this more negative over here and more positive on the other side, creating a discrete pole in the two poles in the molecule. Some nonpolar molecules with polar bonds. We have boron trifluoride here on the left, and fluorine is the most electronegative element, so of course it is going to be grabbing the electrons. But because this molecule is symmetrical, has all the same type of atoms on the outside, it's just going to have a big negative cloud all the way around it, and it's not going to appear any polarity in the molecule, even though the bonds are polar. The same is true of carbon tetrachloride here on the right. Again, the chlorine is more electronegative than the carbon, and so electrons are going to be pulled away from the carbon towards the chlorine, but it's just going to create this negative cloud all the way to the outside, and so you're going to have another nonpolar molecule. The polarity of a molecule will determine many of its characteristics, and we use this every day in cleaning products because polar molecules will tend to dissolve other polar substances, whereas nonpolar molecules will dissolve nonpolar substances. This finishes up what I wanted to say in this last video for Module 9.